Hello students, welcome to this lecture on stick diagrams. So stick diagram is kind of very essential in understanding the overall layout structure, and it also helps in characterizing how much of footprint the design will require. So what we'll do in this particular lecture is we'll go through some of the simple gate structure. We'll start with an inverter primitive circuit, and then we'll go into two input NAND gates and then one more combinational circuit, and then try to analyze or estimate the overall footprint that is required to design that on the chip. To run through the, to run quickly through the basics of the stick diagram, or rather to the basics of the fabrication process. So this is what the slide I have. So what we'll do is in this particular lecture, we will anyways learn the stick diagram, but stick diagram requires some kind of basic understanding or the top view of the overall fabrication process. Right, so in this particular slide, what I've done is I've shown the end diffusions. So let me pick up a pointer. All right, so here is our cross-sectional view of the NMOS transistor. So we have the P well here, and then on the side pockets, we have done the diffusion of N plus and N plus, and the oxide and then the gate. And if we connect, the power supplies onto the gate to the source and then drain to the source, we will have the transistor operating. So this is a side view structure of the NMOS transistor. And here I have represented the top view structure of the NMOS transistor. So if I actually look at, look from this particular side, what I will see is this particular gate, and then on top of this particular diffusion wells, this particular blue box here, which is nothing but the N diffusion, it is nothing but our N plus, which I am seeing here on the side view or the cross-sectional view. All right, and then there is this particular black boxes, which is nothing but this particular P well. Right, so the gate is there, this particular part on the top view side. The red box here is nothing but the gate structure here, represented on the cross-sectional view. Right, so this is what defines the NMOS transistor. So we have a gate, and on either side we have the diffusions, which is N plus diffusion, or also called as N diffusions, and then we have the black box, which is a P well. So what we actually say, when we look this particular view, the top view structure, this gate or the polysilicon gate, so the gate is generally made up of the polysilicon. So I'm going to rewrite it as polysilicon. So that is the material that is that is kind of deposited to form this particular gate structure. So if I have this polysilicon gate running across the N diffusions, then we get the NMOS structure. So from the top view, it looks like this. What it also says is I need this kind of a mask layout. I need this kind of a masks for fabricating my NMOS structure. So masks in the sense, this is, so if I require a polysilicon, so I require this kind of a polysilicon mask where we will have the deposition of the polysilicon only on this particular portion of the polysilicon box. And N diffusion, this is only the portion where I need to do the N diffusion. Right, so only this particular portion is where I need the N diffusion. Right, again, and then P well is, of course, it will be there everywhere. But to talk about the N diffusion and then the polysilicon, this is only the selective process where I require the N diffusion, and this is where I require only the polysilicon gate. All right, although the polysilicon gate, underlying the polysilicon gate, there is an oxide here, which of course in the top view will not be able to see, but that is something which is intuitive in process or intuitive in understanding. So whenever I see a polysilicon gate, beneath that we will have a silicon dioxide layer. All right, so this is how if we give this set of design to the manufacturers, they will easily understand that, okay, this is what the NMOS, the designer requires an NMOS transistor, and this is the three masks are there, which means that I need to follow some kind of a three fabrication process. One is the P well diffusion, the other is the N diffusion, N plus diffusion, and then we have the polysilicon gate deposition. Beneath that, of course, I need to do the oxide deposition. So this is the basic understanding for developing or for designing the Nmos transistor on the silicon substrate. Just to summarize, N diffusion inside a P well defines the Nmos transistors. So N diffusion, this is our blue box on the P well. And if I have a polysilicon gate running across the N diffusion, then we will get an Nmos transistor. Again, the opposite is also true. P diffusion inside an N well defines the PMOS transistor. So of course, what it means is the polysilicon gate running across the P diffusion will give me the PMOS transistor. Hope this is clear. Going forward, so if I want an inverter, right, I will require an Nmos transistor. So this N diffusion and then the polysilicon gate running across it will give me an Nmos transistor. And I'll require a PMOS transistor, so I'll require a P diffusion, and then a polysilicon gate running across the P diffusion will give me the PMOS transistor. And I need the polysilicon gates to be connected, so we will just connect it, the polysilicon gates. And so this polysilicon gate and then this polysilicon gate I'm connecting via polysilicon gate. And this is how my inverter will represent. But it's actually, in terms of the layout, it's a very bad design. The reason is the polysilicon gate is actually running across and then joining the PMOS transistor. So it's better to have this, put it somewhere here. So this particular PMOS structure can be put here so that I will have my polysilicon gate running like this. Right. So what it means is the polysilicon gate should not actually run across and then connect here. Remember that the polysilicon material as such has a little bit higher resistance than that of the copper metal or any kind of a metal. So in that sense, if I have a longer polysilicon gate or a longer polysilicon line that is running to form the gate, I will have more resistance. And to avoid that, what normally we do is the transistors are designed, or rather the inverters are designed in such a way that I will have the PMOS transistor and then the NMOS transistor vertically stacked in the sense in the 2D dimensional footprint. I will have the PMOS and then NMOS very close by. Of course, there will be some kind of a distance between these two diffusions, and the polysilicon will be running, cutting across both the N diffusions as well as the P diffusions. Right? Instead of doing it side by side, we will have it vertically stacked. Right, so that's what we will do. So this particular design, it's a very bad design, but just an understanding that, okay, this is a polysilicon, and then they are connecting. But this takes a lot of space for the gate, and thereby we have this kind of, in a two-dimensional footprint, we'll place the PMOS and then we'll place the NMOS, and then we will have the polysilicon running across it. For an inverter, so this is the schematic of the inverter, and this is the layout of the inverter circuit, and then this is the stick diagram of the inverter circuit. So what we are trying to learn is the stick diagram. So what we'll do is schematic anyways we understand. We will have a look at this particular layout, and then from the layout we'll try to find out the stick diagram. All right. So this is the schematic, the PMOS and then the NMOS transistor connected via an input. So this so the polysilicon of the PMOS and the polysilicon of the NMOS, it's actually indicated by the red box here. So that is the gate. So we have only one polysilicon line cutting across the N diffusion, cutting across the P diffusions. So that means that in the polysilicon gate which is cutting across, the P diffusion should give me the PMOS transistor, and then the polysilicon, the same polysilicon gate which is running running across the N diffusion should give me the NMOS transistor. And we have the VDD rail here, and then of course the ground rail here. So we have the ground metal line and then the VDD metal line, right? And then the VDD metal line should get connected to the one diffusion here. So this is the particular diffusion. So I'm going to write it as the source of the PMOS and then the drain of the PMOS on the other side. So this the polysilicon cutting across the P diffusion will form two diffusion pockets. Could be either of the source or the drain. But here, because this is connected to the VDD, I'm going to call this particular portion as the source. And then this particular portion, I'm going to call this as the drain. And similarly, we will have the source and then the drain for the Nmos. Okay, the source of the Nmos is connected to the ground. So this is the metal line which gets connected to the ground. This is the metal line of the PMOS. From the source, it is getting connected to the VDD rail. And so let me complete this labelings of the Nmos, the drain and the source. So remember that the drain and the drain are connected, and then this is my output line. So the drains are connected. So there is a metal line that is running from the drain diffusions of the of the PMOS transistors, and then connecting to the end diffusion of the NMOS transistor. So this particular metal line is my output node Y. So that is what is indicated in the schematic. All right, so we have completed the VDD rail, the diffusion is getting connected, and then the ground. The polysilicon as such, the length of the polysilicon gate for any kind of technology node is actually 2 lambda. So what it means is for a 65 nanometer technology, it will be actually be 50 nanometers. Right, so 2 lambda represents 50 nanometers in our 65 nanometer technology. So lambda represents 25 nanometers. The metal line, each of the metal lines which are there, so indicating this particular metal line, okay, and then this particular metal line which is connecting the drain diffusion pockets of the PMOS as well as the NMOS transistors, all of them have a length of 4 lambda. They should have a length of 4 lambda. All right. So this is 4 lambda. They should have a minimum length of 4 lambda. The minimum polysilicon, the gate length should be 2 lambda. All right. And the separation between this metal line or this particular metal contact, or I'll call this as a metal line and then this particular as a metal line. So the separation between them should at least be 4 lambda again. So I should have a 4 lambda here, and then of course the separation between them should be 4 lambda. Okay, so these are some of the rules for designing the layout, and these particular rules are called as the lambda scaling rules. I mean, there are different rules, but if you go to one of the particular technology vendors who will actually fabricate and give it to us, so they will try to follow some of the rules, and most popular will be the lambda scaling rule. And so that's what in the layout we are going to do, and that's what we'll carry that forward to our stick diagram representation. So what this lambda scaling rule represents is for any given technology node, if we actually specify the different features of the layout or the stick diagram, right? Different features of the layout, features in the sense the metal dimensions, the metal spacing, the polysilicon length dimensions, and then the metal line, the VDD line, and then the ground line, whatever is the dimensions. If we can actually specify that in terms of lambda, and then we can get it manufactured. But tomorrow, if I want to change from 65 nanometer technology node to 45 nanometer technology node, nothing changes because the lambda is going to change, of course. So if I give the same design of the inverter for a 65 nanometer technology node, the 2 lambda will be 50 nanometers. But if I actually give this, and if I want to design it for a 45 nanometer technology node, then in that sense, 2 lambda will now become close to 40 nanometers. All right. So nothing is going to change, because based on the lambda, the manufacturers can actually enter the what is the lambda value, right? Either 25 nanometers or 20 nanometers. Or if tomorrow, if I want to do for 180 nanometers, the lambda could be 90 nanometers. They can configure or set it, and then we can get the manufacturing done easily. So that is one advantage of doing the lambda scaling. And this is what we are going to follow for the layout as well as for the stick diagram representation. Right. So there's other things, so in this particular sense, what we are trying to address here is one important point, and that is what we are going to follow. The most important point in this particular layout, which we need to carry forward, is the metal spacing and then the metal dimensions. Right. So the metals are the regions where, it occupies more of the footprint or the more of the area. So normally when we design the layout or when we draw the layout, if I want to find out what is the footprint or the area of it, we actually track the number of metals, and then we know what should be the spacing of the metals and what should be the dimensions of the metals, and then calculate the overall area. So even in this particular design of an inverter, which is a very simple 2 transistor design, what we will do is we will have this metal lines. We'll calculate the number of metal lines. So in this particular case, VDD is one metal line, and there is a contact here which represents that this particular contact, and then this particular contact, which which ensures that there is a vertical contact running through the diffusions and then coming above and then connecting the metal lines. So these particular contacts are also called as vias. Okay, so all this, the small boxes with the colored boxes is nothing but vias, is the vias. So what is the vias is nothing but if I have a diffusion underlying this particular layer is the diffusion, and then I will have a metal line that is running across it. So I'm trying to draw a design, and this has to connect to this particular diffusion so that I will get the current that will be running across it and then running across it. So this particular portion is called, it is called as a vertical metal wiring. So what we do is there's some kind of an etching process and then filling process, the metal filling process. It's very simple chemical process called as the plating process. Electrochemical plating will be done to fill those regions. And then it will form the vias. But anyways, in the top view, we will not see the vertical lines. What we'll see is a small square box, because this vertical line will be seen as a small square box in the top view, and that's what is represented in the layout. All right. So coming back to the number of metal tracks, so what we'll see is this VDD is one metal track, round is another metal track, and then this contacts which says that okay, there should be a metal line that should start from the diffusions of the source and of course the drain of the PMOS gets connected to one gets connected to the VDD, the other one gets connected to the Nmos transistors diffusion. Similarly, I will have one more metal contacts here. Which is on the source and the drain side of the Nmos transistor. On one side it gets connected to the ground, the other side it gets connected to the drain of the PMOS, and then the fourth one is the ground rail. So that is another metal line. That is on the vertical side. So that's on the on the horizontal side. So I have 1, 2, 3, 4, and what we know that the metal. The dimensions of the metal. So in this sense, the width of the metal in this case should be at least 4 lambda, and then the spacing. So the spacing between this and this should at least be 4 lambda. So again, the spacing between this and this should be at least be 4 lambda, and then the spacing between this and this should at least be 4 lambda, and the width of this particular metal line should be at least be 4 lambda. Similarly, on the horizontal, on the vertical side, we have one metal line. So this is one metal line, and then we have this particular one metal line. So I'm going to write it as 2. the length of this particular metal line should be at least be 4 lambda, and then the spacing should be 4 lambda. That's what I have reiterated. All right. So this is what we have, and then we will now draw the stick diagram. We'll try to understand the stick diagram representation. So we have the layout drawn for the inverter. And that stick diagram is basically a very handy rough estimation of the footprint. It doesn't provide the details, but it just provides you, where does the polysilicon gate line is there, where is the metal line going around, and what is the overall footprint, right? So if I want to actually draw all these boxes instead of boxes, right, if I want to represent it by a line, that becomes much simpler for our rough estimation. So instead of the VDD, a metal box here that is being represented by a single line, ground rail, which is a box here, which is represented by a single line, and then the P diffusions here, which is represented by again a blue box here, and then the N diffusion, blue box here, is represented by a single straight line. So P diffusion and N diffusion, and this vias or the contacts which connects the one diffusion to the VDD rail and then one diffusion to the ground rail is actually represented by a cross and then gets connected to the VDD, represented by a cross and then gets connected to the ground. The polysilicon gate, which is which is kind of a box, is represented by a straight line again. So a red line with an input saying that this is the polysilicon line. And the other side of the diffusion, the diffusion of the PMOS and then the diffusion of the Nmos gets connected by a metal line, which will also be indicated by a straight line. So all the boxes in the layout is actually now represented by a straight line, and that forms a stick diagram, right? Of course, the vias or the metal contacts are actually indicated by a cross symbol, just to say that okay, there is a metal contact between the above rail VDD and then the diffusion P diffusion. And similarly, there is a cross here which represents that there is a metal line that is running from the ground and connecting the N diffusions. All right. So this forms the stick diagram. It looks pretty simple. So looking at this particular stick diagram, there are not multiple boxes. It's a single straight line. And so looking at it, we can easily characterize the layout of any circuit what we have drawn. So the layout as represented in the last slide, it's too detailed and works well in the software. So if we have a particularly good software, I think we will be able to draw the layout very nicely. But for rough, handy area estimates, stick diagrams are recommended. Right. So in terms of the paper design, so if I can easily draw it on the paper and then give you a very rough estimate of the stick diagrams. And if you want to optimize in terms of the area, we can actually redesign our circuit and then once again do a rough estimate in terms of the area on the paper and then find out which design is appropriate. So this is what we have. So we for the layout in the last slide, what we had indicated the number of metal tracks horizontally and then vertically. The same thing I have represented in the stick diagram here. So in the stick diagram, vertically, this is the number of the horizontal tracks. So 1, the VDD rail, 4 is the ground, 3 metal line, which is nothing but the contacts. Second is again the contacts here. So I need to have, so each individual line of the metal line here is actually 4 lambda. So each individual line, the width of it is 4 lambda. And then the spacing between the metal contacts should be at least be 4 lambda. All right. And similarly, the number of vertical tracks. So here it is 1 because there is one metal line connecting the VDD to the P diffusions and then the N diffusions to that of the ground. And then there is one metal line which is connecting the diffusions of the Nmos and the PMOS, making it the output node. So that's what I've written horizontally. We have 2 tracks, right? So horizontally 1, 2, 3, 4. Although I've written it as 2 tracks of metal and 2 diffusions. What is actually the diffusions are there, but it's basically the metal contacts on the diffusion which which gives me 2 additional metal tracks. So thereby making it the 4 tracks, and vertically I will have 1 and then the 2. So 2 tracks of metal. Each of the metal line should have a minimum of width of 4 lambda, and then the spacing to the next one should be 4 lambda. So we can consider, if I have one metal line in the stick diagram, I can consider that it is to be occupied of 8 lambda, right? It occupies at least an area of a spacing of 4 lambda plus the width of 4 lambda. So it will give me an occupation of 8 lambda. So the next metal line should come after 8 lambda. Right. So in terms of area, it is actually 2 into 8 lambda multiplied by 4 into 8 lambda. So, whatever is that, lambda will be nothing but 25 nanometers for a 65 nanometer technology node. Each metal track is of width 4 lambda, and then the spacing is 4 lambda with the other metal or diffusions. Right. Now, one may always argue that, this particular metal spacing will start from 4 lambda. So if I can actually do the calculation, this is 4 lambda spacing, and then from here to here it is again 4 lambda spacing, and then from here to here 4 lambda, and then the 4 lambda width here. So it is actually 4 lambda. Of course, the width here is 4 lambda, and then the width here is 4 lambda. Right. So the 4 lambda, and then if I do it, it will be nothing but this 4 lambda plus this 4 lambda is my 8 lambda plus this 4 lambda plus 4 lambda is 8 another 8 lambda, and then this 4 lambda, and then this 4 lambda is 8 lambda. So 3 into 8 lambda plus this 4 lambda, and then we don't require any more spacing of 4 lambda here. One may quite argue that why is this 4 lambda is required. The reason is normally a chip will not have only one inverter circuit, so we will have one more circuit below this or on top of it. In that sense, if I want to start one more circuit here, I should, there will be one more diffusions or a metal line that will be running, and the spacing of 4 lambda is very much required, right? So in that sense, to be very, very conservative, we will have this 8 lambda for each of the metal lines, and then whatever is the number of the metal tracks, I'll get it multiplied. Now the other question is, why is this 4 lambda, the least that is required to design the metal track? I know this is coming from the highly calibrated fabrication process. So if I actually don't have the 4 lambda, and let's say that if I have a 3 lambda, the process itself has some kind of a deviations. So if I actually want to have, let's say, 3 lambda of a metal line, right? So we will design the process. So the process is highly calibrated and highly characterized. And after the process, is done, what we might actually get is a 3 lambda plus minus, some values in terms of nanometers. So we cannot actually get thoroughly 3 lambda. So it will always be characterized with some small amount of deviations, right? And it has been, the process has been so much studied or investigated that with the 3 lambda of metal spacing or a 3 lambda of metal width, it doesn't give the best results, whatever we expect it to. So hence, we, the minimum width or the minimum length of the metal track should be at least be 4 lambda. And even if with the 4 lambda, we will have some kind of a deviations, 4 lambda plus minus x deviations, it is likely to give a better results. All right, hope this is clear. Moving forward, this is the two input NAND gate circuit, and then we want to draw the schematic of this and then try to identify what is the overall footprint. So the schematic of the 2 input NAND gate, as we know, it is 2 of the transistors in series and then 2 of the transistors in parallel, A and B. And if I want to draw the stick diagram, so I will anyways have the VDD rail, I will anyways have the ground rail, and the P diffusion and N diffusions are there. The polysilicons which will cut across the P diffusions and N diffusions forms the Nmos and the PMOS transistors. right? So here we will have the A polysilicon. So basically this A and then this A are connected in the schematic, and then this B and then this B is connected in the schematic. So I will have one polysilicon line which will cut across the P diffusions and N diffusions, right? So that means that the P diffusions on one side of the diffusion, so on one side of the diffusion, it gets connected to the VDD. So this is what is getting connected to the VDD. And then on the other side of the A polysilicon, so this is this particular side I'm talking about. So this is this particular side, and I have a cross here. Of course, there is a cross here also, which says that, okay, this is connected. There is a metal line that is connecting to the VDD rail. This cross is this particular cross, which is the output node. So I can write it as the output Y. This particular output node is a common node between the B transistors on the B PMOS transistors on one side of the B PMOS transistors. This one. In fact, I'll write it as the drain, and then the drain, and then the source, and then the source. Right. So the drain of the B and the drain of the A transistor and B PMOS transistors are both connected, and that is the output node. So that is what I have written here, the output node. So the B polysilicon, the other side is the source one, source diffusion, which gets connected to the VDD. Right. So in this particular case, this particular diffusion is a merged diffusion. Right. It's a merged diffusion and it's a contacted diffusion. Right. And this particular contact is our output contact, which actually goes to the A transistor on the Nmos side. So A transistor N diffusion and then A polysilicon gate cutting across it will give me the A transistor on this particular side. On one side, it is it is in the diffusions of the A transistor and then the diffusions of the B transistor are merged together, but there is no contact there. So that is this particular point. So the B polysilicon and the A polysilicon, whatever is common here, so that becomes our this particular point in the schematic. And then we have the other side of the B transistor, which is connected to the ground. So the other side of the polysilicon of the B is this one, which gets connected to the ground. Right. So I have now the output node Y, which gets connected to the one side of the diffusion of the A transistor. So the output Y node gets connected to the one side of the diffusion of the A transistor. So that is this particular point. Okay, so this completes the stick diagram. What are we interested in? We are interested in the area or the footprint. So let me track the number of metal lines and of course the diffusion lines. So let me start, from this particular side, the horizontal side. And remember that this particular horizontal side, or this particular dimensions is the width, and then this particular dimensions is the length. Right. So in terms of the width, I will track number of metal tracks horizontal metal tracks. So this will be the one metal line, the VDD one. Fifth one is the ground metal line, and then we have the two diffusions, 2 and 4. And in between there is an output node, which is the third metal line. So I will have 5 tracks multiplied by 8 lambda. Right. So 5 tracks multiplied by 8 lambda. On the vertical side, I will have the number of vertical tracks will be 1, and then there is one here which can be aligned with this one, and then there is one here which can be aligned with this one, and then there is one here which is the second one. So 3 metal tracks running vertically. So that will be 3 into 8 lambda. So for a P, for a size of 1:1 PN ratio, so 1:1 in the sense, if I have a size of 1 here, 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 right, ratio for a 2-input NAND gate, then I will have this 5 into 8 lambda, 3 into 8 lambda, multiply that will give me the footprint. But suppose I want to have an equal falling resistance and an equal rising resistance with that of the 2:1 inverter. In that sense, I need to have, instead of a size of 1, I need to have a size of 2 here. I need to have a size of 2 here. I need to have a size of 2, and I need to have a size of 2. What it implies is the end diffusion, which we were considering it to be 4 lambda, right? 4 lambda represents 100 nanometers in the 65 nanometer technology. So that represents the scale of 1, right? So for a scale of 2, it should be nothing but 8 lambda. And then similarly here, the P diffusions, the scale of 2 represents 8 lambda. Right, so we were considering 4 lambda and then we were calculating the number of metal tracks multiplied by 8 lambda, because 4 lambda is the width and then additional spacing of the 4 lambda. Here now, because the scaling is 2, the width of the diffusion is 8 lambda and the additional spacing of 4 lambda is required. So what we have is an area which is kind of increased by 4 lambda on the PMOS side, on the P diffusion side, and then 4 lambda on the N diffusion side. Right. So this is what I call it as accommodating the increased diffusion widths.